Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics.
Welcome to Speaking of Reliability. This is Carl Carlson.
And this is Chris Jackson. We're going to talk about requirements based on a listener, I believe, Carl, who asked a question about RPN and FMEAs.
Yes, and it's amazing how the question got into requirements, which surprised me when I was.
I'm looking forward to you joining those dots for me.
Yeah. So a listener asked a really good question, which he was, in fact, all the questions I get are very good. But he had a mandate or a decision from management to develop reliability requirements from the RPN on an FMEA. And then they had a caveat that if that didn't work out, then maybe use the calculations from the FMEA, the criticality assessment. And he asked me, what do I think? Well, you can imagine, Chris, I had a lot to say on that. And I'll just enter a couple of things, and I'd love to hear your thoughts. RPN, first of all, I do not any longer recommend RPN in an FMEA. And that's a subject of its own, but just the 15-second summary there is RPN's made up of severity, occurrence, detection, and the multiplying them together does not give you a risk metric, because very often high severity and low occurrence can be very high risk. And so the RPN has flaws in it, becomes a numbers game, and I don't like to use it. I use I'll call it a combination of SOD on some type of matrix that seems to be more useful. So that said, the RPN and the constituents of RPN are subjective. They're not objective. So when you have an occurrence rating, it's not like you're saying the reliability or the probability is X to a couple decimal points. It's a subjective rating so that you can then assess the risk. And therefore, we should not use it as a reliability metric. And I wrote that back to him, but I also said on the FMEA side, the calculation that's done in FMEA, which includes the failure rate, during the time when FMEAs are normally done, you often do not have accurate failure rate information on the subject that you are analyzing, because it's a new design, new technology, that type of thing. So I wrote back that, and then I thought, well, I should tell them how to, what's the right way to go about setting reliability requirements. But what I did is I said, stay tuned, because we could make it part of a podcast. And so here we are on the podcast. Anyway, your thoughts, Chris, on the subject?
Well, just a couple of things. I mean, I find it's nowhere in any standard does it say that a FMEA, which includes a criticality analysis, has to use failure rates. If you look at the FMEAs, standards that mention FMEAs, they simply say the criticality analysis is simply the way of quantifying the risk. But it seems that the industry has believed that all FMEAs with the C in the title must include failure rate estimates. That's just my thing. In fact, in Europe, they don't do that. They don't have a separate acronym for FMEA or FMEAs. If they have an acronym that's just very FMEA centric, because it's just all about, they're all the same, seen as the same thing. That, be that as that may. I suppose one of the questions I would ask is, why are we doing requirements after we do a FMEA/FMEA?
You mean the timing?
Yeah. So if you're creating a product, let's just say the microphone I'm talking into right now, the consumer product, you know that to make money, you can't have a warranty reliability, for example, which is much less than 95%. It depends on the industry. Some industries, you can't have more than 1% of your things failing during a warranty period for you to have any hope of making a profit. Other industries, it's 10%. So there is, regardless of what your FMEA or FMEA comes up with, there is this inherent requirement from the customer perspective, which trumps everything. Is that a fair call?
Yes, indeed. And your point is very well taken. The reliability requirement needs to be up front right at the beginning. The time you're doing the FMEA, and I'll use FMEA rather than FMECA because FMEA really does include criticality analysis.
Hmm.
Time you're doing the FMEA, that's not the time you want to be developing requirements. You should have requirements going in
Right,
to the beginning of the program. And then the FMEA basically says, let's make sure the design is robust and
right.
meets requirements. So it's kind of backwards to use the FMEA to develop reliability requirements, even if it was possible, which it isn't.
And let's go one step further. When you do FMEAs properly, you customize your severity, occurrence, and detectability scales. So a seven, that means you might have 1 through to 7 different levels of severity in some scenarios. Sometimes it's 1 through 4 if you have a very simple product. Sometimes
Yeah.
it's 1 through 10. But you should define those severity levels. And of course, when you're doing a nuclear power plant FMEA, the severity 10, I would imagine, is quite severe. But when you're doing the FMEA for the microphone I'm talking into right now, well, a severity 10 failure is going to be very, very different in terms of its effect on society. Let's just call it that. Same with occurrence. For a nuclear power plant, it's supposed to operate for decades without critical failure. The microphone I'm talking into, it has a 2-year warranty. So very, very different. And sometimes you do include detectability, sometimes you don't. I think it's good to include it. However, I tend to shy away from it when I'm dealing with sort of for me a meat, so to speak, just to try and keep it simple from the start. And then maybe once they become more fluent with severity and occurrence, maybe we'll throw in detectability. But there is no, there's not supposed to be a universal scale of severity or occurrence between different products. It's supposed to be a tailored table which uses language which is very specific to your product in order for your workshop to very quickly settle upon a score from 1 through to 10 or whatever the scale is. I've seen plenty of scenarios where they use, for example, the 4 levels of severity from mill standard, that's the FMECA mill standard, where they try to apply that to everything from radios through to warships. And
Right.
it's just not possible because you talk about things like mission failure or weapon platforms going down. And you say, well, if the radio doesn't work, maybe the general can't communicate to the artillery battery over there, so therefore the weapon system is down if the radio doesn't work. And all of a sudden, you use that line of thinking, and then every single radio failure becomes a catastrophic severity because someone can imagine a scenario where these very sort of general ambiguous definitions in a standard just don't fit. Um,
Yeah,
so,
and actually, just thinking about this for a minute, Chris, the the purpose of the risk ratings in a FMEA is not an objective in its own.
no,
It's basically a path to get to improvements. So you
right,
risk rate so that you can prioritize risk so that you can get to recommended actions and actually reduce the risk.
right,
That's the whole purpose of it. So people that think it's an end of its own, like it results in reliability requirements, they're missing the whole point of doing it. It's not,
right.
like as you point out, it's very different depending on what product you have and how it's used. But let me get to the other side of the question. How should, and I've got my own thoughts in it, but I'd be interested in yours here. What's the right way to go about developing reliability requirements?
Well, I think there's a couple of things at play, but look, a good example would be the one I just talked about for the microphone warranty reliability. You don't, if you don't know how many warranty failures you can tolerate before you start losing profit, then your business case is a shambles. You need to know exactly how many things can fail during a warranty period before you start losing money on that product line. And that's a um, business-driven requirement. And I think what happens a lot is people who think they're good at business, the managers and the CEOs and the like, don't want to actually have that conversation. And so they push it to the reliability guys and girls. So you come up with a requirement and they say, well, all right, so how many things are allowed to fail in the warranty period before we start losing money? And not a lot of organizations actually know that. And until you do, you can't come up with a warranty, for example, warranty reliability. So that's one. Another one I'd suggest is important is if I was putting requirements together for my microphone, I would consider having a separate reliability requirement for the early failures, the first 3 months worth of failures, because those are catastrophically bad for your brand. It's one thing having a microphone fail 5 years after you purchased it. It's annoying, got it, but I would argue that many customers can be sort of rational about understanding what a 5-year failure is versus a 1-year failure, which might be subject to warranty repair, versus a 1-month failure. A 1-month failure is uniquely terrible in the eyes of a customer because it pushes the narrative that this is a piece of junk. And so that's much worse than a 1-year failure or a 5-year failure. And so I often like asking clients to consider a 3-month reliability target or a 6-month reliability target, because that then sends a message to the design team, hey, we need to be on top of infant mortality or wear-in failures as well, because they are really bad. And it sort of pushes us towards making sure that we keep our manufacturing team in the conversation as well, as a lot of infant mortality issues stem from defects during manufacturing. And a rule of thumb, 80% of manufacturing defects have their headwaters in design. So there's two I'd throw out there. Is that anywhere within your
That's good.
realm?
That's good. That's a good. Those are good things to consider. The early versus the later, and they obviously have different. I'll use the word severity, but I don't mean that just in the FMEA sense. They have different consequences to customers. Obviously, safety is another differentiator. A failure that is potentially catastrophic will have to have a much higher reliability requirement than a failure that's a nuisance, no matter when it happens. If it happens early or late, obviously safety is going to be its own. In fact, when I was at General Motors, we would have extremely high reliability for safety and almost not measurable, because it would be 99.99, et cetera, on airbags and things like that. Essentially zero failures, although that's not possible to demonstrate. And then a different set of reliability requirements, I'll call it performance. But even performance could have performance of the main function or some type of annoyance thing. And so they have to be set with the customer in mind, as you're pointing out, the timing in mind, which you point out. I'll also state something, and this will take a little story. I'll start with the story. At General Motors, early in the 1990s, we were focused a lot on suppliers because we didn't have enough emphasis on suppliers. And to get reliability from suppliers, we had to have good reliability requirements. So that sort of put that on my radar. I was manager of product reliability at the time in the early 90s and said, okay, I looked at our reliability requirements. The requirement was DPTV, defects per 1,000 vehicles. Now that's a very field-oriented requirement, hard to measure. So when and we actually tried this. We said, okay, supplier of hinges, you have 0.04 DPTV, and that's your requirement. And then the reliability group back then, before I took it over, said, we did our job. We gave them a
Yeah.
reliability requirement. They're allocated 0.04 DPTV. And I'm thinking to myself when I saw those documents, that's a worthless requirement because it's not
Right.
measured. And so one of the characteristics of reliability requirements, I think, is it needs to be measurable. So I just wanted to share that story and that characteristic.
The problem with that, though, is that when it comes to measurable, when you have very high reliability requirements, or even a warranty, say you want to have a 95% 3-year warranty reliability, that can be hard to measure, because when you say measure, people immediately think of testing until failure, and very demonstration testing centric, where I believe we're on the same page. But let's look at the door handle of a smart lock, because I often use the smart lock as a case study. But a door handle in this smart lock is made from an alloy, a steel alloy, which can be subject to fatigue. And let's just say we do FEA, finite element analysis, and find that in the inner radius of that door handle, where you have that stress concentration relatively high, the computer said it was able to say, you know what, the maximum stress that the inner radius of that door handle experiences is 500 megapascals. And for an SN curve associated with that steel alloy, I think let's just use 1045 in this case, in this story. Well, you can then get the SN curve and look at the cycles to failure distribution from the SN curve and say, okay, no worries, the 10th percentile cycles to failure, or door openings to failure for my smart lock is 87,000. That means that we expect 10% of these things to fail due to fatigue from after the handle has been turned 87,000 times. That means you can go back to the use case and say, okay, how many door handle openings are we expecting per year, per month, what have you, and come up with the number. And so that's one way to quantify it. Another thing you can do is say, hang on, well, the thing about steel is that it usually has this endurance limit where below a certain stress, fatigue never happens. And you go, okay, well, why don't we change the design so the inner radius isn't as sharp, reduces the stress concentration. Now, let's look at the SN curve, and lo and behold, for the SN curve at 1045, still the endurance limit is about 300 megapascals. And so that means that if you can reduce the stress to below 300 megapascals, fatigue will never occur, because we studied steel that well. And so we changed the design of that handle such that we can, in a way, demonstrate that fatigue will never occur, and that's the dominant failure mechanism for that handle. So I would argue that the latter is a scenario where we can't measure the reliability, but we can show it's very reliable. So would that align with you can still have a requirement that's not measurable, so to speak, in that context. Would you agree?
Yes. And I would characterize that as measurable from terms of a compliance. In other words, you're going to be very good reliability. You're going to be at least 95% or better is your judgment based on, and that's kind of what I mean by measurable. In other words,
yeah,
you may not get an exact number, so I should probably use a different word, but you'll know whether you meet it or not. And that's what I'm talking about. Whereas when we sent out the letter to suppliers that they had 0.04 DPTV, that was not directly measurable unless you had a really good reliability engineer that could take that and break it down into the science that you talked about on the SN curves and et cetera, and develop a test plan or an analysis plan that actually showed that you met that requirement. So that brings me to a kind of a comment about your comment, which is you really do need reliability engineering expertise when you're talking about reliability requirements. Because if you just put out a number, but you don't have the expertise behind it, then you have no way to demonstrate it.
Well, the other thing too is when demonstration, that's a term. That demonstration is a term which has no definition in reliability. But it's almost like a FMEA, but when people say reliability demonstration testing, there is always a chapter dedicated to it in a textbook because the statistics come out because it's implied that a demonstration test is all about time to failure tests in at-use conditions where you can sort of demonstrate in a very not a simulated way. You're not allowed to do anything to try and change the operating environment. Militaries love demonstration tests. They'll have vehicles they test for years to try and demonstrate reliability because it has to be in at-use conditions on test tracks and everything else because that's the only way you can find things that are reliable. Just on that note, Joint Light Tactical Vehicle designed by Oshkosh did very well in the demonstration testing, exceeded the requirement by a factor of 3. But lo and behold, the Joint Light Tactical Vehicles the US Department of Defense purchased weren't very reliable because manufacturing wasn't good. And so we have a design which is very reliable, demonstrated to be very reliable. Then they stopped taking manufacturing seriously. And the US military said, you know what, we're going to take your design and get somebody else to build the vehicle that you designed, which you've shown was reliable because we've lost confidence in you being able to manufacture it without defects. Which just goes to show that there's no point demonstrating reliability to that extent because there are so many factors at play thereafter which influence reliability after you have a design. There's no point designing something amazing if you're going to have lots of defects in the product. And the reports that were released weren't talking about unanticipated or crazy failures. No, just brakes not working, wiring issues, just automotive 101 sort of thing. But as a slight aside about demonstration.
Yeah, very good. Very good. Good comment on demonstration. A couple comments to share with you here. One of the things I've learned is that from that General Motors experience and that I've taken with me throughout my career is that we want reliability requirements to be folded into technical specifications. Back in the day in the 1990s, we had reliability requirements as a separate memo. Right. And we want them to be actually in the tech specs. They're part of bids if you go out to suppliers. They're part of internal testing and analysis. Right. But I also want to emphasize, and I know you know this backwards and forwards, but I'll mention it to our listeners, is that when we talk about reliability, especially reliability requirements, we want to understand the definition. And so the definition, Fred and I talk about the big 4 elements in the reliability definition. So you have the probability that the item will achieve the intended function. That's the second one. So you got a probability aspect to it. You have an intended function aspect, and then understated conditions. So that could be operating environment, customer usage, whatever the conditions are of operation over some period of time. So good reliability requirements have to have at least 4 aspects to them. And oftentimes I find 1 or 2 or sometimes 3 of those missing. Sometimes people think, well, just put a probability number on it. I go, no, you got to have the intended function. You have to have the conditions of use. You have to have the time aspect. And when you get all 4 of them, now you have the opportunity for good reliability requirements. So I wanted to share that to the listeners as well.
Well, sort of go back to that initial comment about the FMEA where failure rates were going to be used. Failure rates, you don't want to have failure rates as requirements for subcomponents or components or subsystems. For example, let's just say in your FMEA, somehow you come up with the requirement of a failure rate for a bearing. Well, bearings wear out. So an MTBF for a bearing that you get off the shelf usually means that's a point. It's a balance point of all the data, all the failure points. And so the MTBF or MTTF is, from a statistical perspective, is the time by which anywhere between 50% to 80% of your things have failed. And a lot of bearings you don't run to failure. You actually have bearings replaced at fixed intervals, or you have condition monitoring where you're listening for vibration and heat signatures to find out when spalling is starting to cause a problem, then replace those bearings preemptively. So those ball bearings, if they were those ones that you're replacing through preventive maintenance or predictive maintenance, if you were to put them into a test bench and essentially measure their MTTFs, you come up with the cycles to failure. But once you start using preventive maintenance or predictive maintenance, well, the apparent MTTF is going to go through the roof because you are preventing failures. Yes, you're replacing bearings before they fail so still working bearings with brand new bearings, but that's cool. Now, why is it a concern? Well, if you just say, well, we need to have an MTTF of 2 million cycles for your bearings. Okay. Well, one way of doing that is to, if you never replace your ball bearings or your bearings or anything like that, well, then you're going to need to have incredibly, and you just use the MTTF based on its pure statistical sense in terms of, I need the MTTF of the ball bearing to be 2 million cycles, where you're going to have, in some cases, a very heavy, very expensive ball bearing. But in the real world, that's not what you want. You actually want a ball bearing with a statistically much smaller MTTF that you're going to routinely replace at fixed intervals or use condition monitoring predictive maintenance to address. So the apparent MTTF could still be 2 million cycles, but with a much less expensive, much smaller ball bearing that you're monitoring as you go, and you replace most of them before they fail. And yes, failure is always an option. So as soon as you break it down into MTTFs for bearings or anything else, it just takes away the actual nature of failure and the fact that failures, we do everything possible in many scenarios to prevent failures that are going to occur. And so MTTFs are bad. There's a summary of that little
very, very good. And which is really important when we're discussing how you develop good reliability requirements. We need to state that even though we've podcasted on this before and you've done great webinars on the subject, the MTBF is a big issue, has a lot of flaws, which brings up one of the aspects to consider about requirements, which is what assumptions you have going in. And be careful, obviously, of the exponential distribution assumption, for example. Right. But I think we've covered at a high level, this is a much deeper subject than one podcast, but at a high level, some of the aspects to consider about setting good requirements for reliability. What should, if I would love to hear from listeners on this, as to what kind of requirements you have in your companies, in your organization, what questions you have. What should they do if they want to get in touch with us on that subject?
Well, of course, both you and I, Carl, we have our contact details on the Ascendo Reliability website, and I think people who listen to us enough know how to reach out. But for those people who are new or veterans who have forgotten how to reach out, feel free to go to www.ascendoreliability.com/go/SOR, and that will take you to a page where you can do everything from sending us a message to a recording a voice message that we will be able to hear from you if you've got any ideas or follow-on questions, because as Carl pointed out, we've just sort of scratched the surface in this short conversation, but hopefully it's been of use to the listener or the person who reached out.
All right. Well, thank you for that, and I enjoyed talking to you, Chris.
Well, always a pleasure, Carl.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.